Hello, this is Jack Jackson. In this video, we're going to be talking a little bit about the ratio test for testing for convergence or divergence of series. So notice that the direct comparison, limit comparison, and integral test all require the terms of the underlying sequence to be positive, or at least be positive from some point on to the right forever. Sometimes we have terms with negative terms, or a mixture of positive and negative terms. Sometimes even a random kind of mixture. If the series, the sum from k equals 1 to infinity of the absolute value of a sub k converges, then the sum from k equals 1 to infinity of a sub k also converges. And we say that the series converges absolutely. Absolute convergence is actually stronger than just convergence, because if a series is absolutely convergent, then the series is convergent. However, there are some series with a mixture of positive and negative terms that converge, but they're not absolutely convergent. These series are conditionally convergent. We will revisit the concept of absolute convergence versus conditional convergence a bit more in a couple of sections from now. In the meantime, we will be considering the ratio test. The ratio test does not require the terms of the underlying sequence to be positive. When the ratio test determines that a series converges, it will actually conclude that the series converges absolutely. So recall that a series of positive terms will converge only if the underlying sequences of terms approaches zero fast enough. All of the series convergence tests can be viewed as determining how fast enough is. In this context, the ratio test says that if the sequence is approaching zero fast enough, then the ratio of one term to the previous term should be approaching a small limit. How small? Well, this limit has to be less than 1. If this limit is larger than 1, then the series is going to diverge. If the limit is equal to 1, the test is inconclusive, reaching no determination, so we'd have to use some other series. So here's the ratio test. We let the sum from k equals 1 to infinity of a sub k be a series with non-zero terms. So if there are any zero terms, we'll just sort of yank them out. And then we can do the ratio of successive terms. So we take the limit of a sub k plus 1 over a sub k, take the absolute value, then take the limit as k goes to infinity. You can see why we want their terms to be non-zero, because we don't want to be dividing by 0 here. If that limit turns out to be less than 1, then the original series up here converges absolutely. If that limit turns out to be greater than 1, or if it doesn't have a limit approaching infinity, if it's specifically that, then the series diverges. And the ratio test is inconclusive when that limit is equal to 1. So here's a proof of that. Suppose that the limit of those terms is some L, which is less than 1. Let B be a constant between L and 1, so B is less than 1, right? And a positive number for that matter too. So by definition of a limit, there's some n greater than 0, such that if k is greater than n, then this thing here is got to be within within n of that. So within epsilon of that that limit. Well, epsilon is our b here, right? And so the L is less than this thing here, which is less than B. Okay, and so this tells us that the A sub k plus 1 term is less than B times the absolute value of A sub k. Let's take this part of it here and multiply by that. And this is for some k, for all k actually greater than n, this is going to be true. Okay, well, let's take a look at that just a little bit. So if we take the n plus 1 term, capital N plus 1 term, that has to be less than b times the a sub n term. And then the a sub n plus 2 term has to be greater than, or I'm sorry, less than b times the n plus 1 term, absolute value. But wait a minute, the n plus 1 term was less than b times a to the n, absolute value. So we have b, we multiply, we can replace this by b times that, and it's still less than, so that's b squared times a sub n. And then the n plus 3 term is less than b times the nth term, n plus 2 term, absolute value, but that is b squared times the n plus 1 term, which is b cubed times the nth term, and so forth. So in general, we get the n plus capital N plus lowercase nth term of this a, absolute value, has to be less than b to the n times the absolute value of a sub n. Okay, so this is basically following from the basic limit definition for a sequence. Okay. All right, well, therefore, by direct comparison, we get that this series here, the series from that point on at least, from capital N plus 1 on, that is less than b to the n times the absolute value of a sub n, or at least less than, let's say less than or equal to at least. Sometimes when you take limits, you could get equality there. However, this one here on the right side is just a convergent geometric series. Remember, a sub n is a particular term, right? There is some n that we've identified up here, capital N. So that's a particular term. That's constant. It's not changing as little n is changing. So that's just a, a first term of b times a sub n, absolute value there, is the first term, and then each term after that it's multiplying by another b. So this is just a geometric series, and it's convergent because where's b? B is between 0 and 1. Okay, so therefore, this series right here converges by direct comparison to this geometric series. But then, of course, what's the sum of a sub k? Well, it's the sum of the first capital N terms, and then from capital N on to infinity. If infinite tail converges, then certainly the whole thing does, because that certainly sum up any finite number of terms, that's convergent to a particular number, of course. And so we were talking about absolute value all the way through here, so we see that this converges absolutely. Now, to get the divergent part, it's kind of similar. If it reaches some limit which is greater than 1, then if b is a constant between L and 1, so now b is bigger than 1, or if L is infinity, we could choose any b greater than 1. And by the definition of a limit, there's a sum n greater than 0, that if k is greater than n, then our ratio, which equals this, is approaching this limit, has to be bigger than b, right? It has to be closer to 1 than b is. So it has to be between b and L. Okay, same kind of thing that we had up here. If this limit is L, that has to be close to b. How close? Well, at least closer than L is to it, right? It has to be closer to L, I'm sorry. But how close? At least closer than b, so it has to be in between there. Okay, so moving right along down here, where was I? Okay, so we have, again, we have this setup right here. B is less than this ratio, absolute value less than L. Multiply both sides by absolute value here, specifically this left side here. And so we get the B times this sum is smaller than the B times the a sub k is smaller than the a sub k plus 1. So the absolute value of ak plus 1 is greater than b times absolute value of k. And we get the same setup that we had before, but now the inequalities are right in the other direction. And the other thing is that b is bigger than 1. So we now get our sum of that tail is greater than a divergent geometric series because now b is bigger than 1. And so then the series is diverges by direct comparison. And that finishes up. Notice the case we didn't do was when b equals 1, and of course that means the ratio test is inconclusive. Now ratio tests is a really nice test for us. We're going to use it quite a bit. And it works especially well when the series involves factorials or exponents with variables in them, because we can get a lot of nice canceling out when we look at ratios of successive terms. So here, let's put this to work in a couple of examples. So the first example we're going to look at is the sum from k equals 1 to infinity of k factorial over k to the k power. And the second one is 2k factorial over k to the 6th. Okay. First, let's just see what intuition might tell us. K to the k should be growing faster than k factorial. So this probably should be approaching 0 fast enough that the underlying sequence should be approaching 0 fast enough so that the whole thing is going to converge. But let's work this out and prove this with the ratio test. Okay, so what you do with the ratio test is you plug in k plus 1 where all the k's are, and that's the numerator, divided by, and then the original thing is here, absolute value of the whole thing, take the limit as k goes to infinity. Okay, so let's look at this thing here. What's in the numerator here stays there, k plus 1 factorial. This goes to the bottom, k plus 1 to the power k plus 1. That k factorial is there in the bottom, and the k to k here flips up to the top there. All right, so we end up getting some canceling. The trick is that k plus 1 factorial is k plus 1 times k factorial. Okay, and k plus 1 to the k plus 1 is k plus 1 times k plus 1 to the k. Remember our property of exponents there and our definition of factorial. Well, the k factorials cancel. That's nice. This k plus 1 and that k plus 1 cancel. So what's left? The k to the k in the top and the k plus 1 to the k in the bottom. Since everything is to the k, we can sort of bring that out here and make this k over k plus 1 to the k. Now we can, inside here, multiply by 1 over k in the top and bottom inside this parentheses, and that's 1 plus 1 over 1 plus 1 over k to the k factorial. And then, of course, 1 to the k is just k. That doesn't affect anything on the limit, so that's just 1 there. And then we have the limit of this bottom. So we have the limit of, as k goes to infinity, of 1 plus 1 over k to the k factorial. That's the definition of E. Okay, so think back, way back to when we first introduced E and first introduced exponential functions in calculus when we were deriving the derivatives. We introduced that, if you might look back at my earlier video there. So this is what we needed E to be so that the derivative of E to the x would be E to the x. So this limit is a constant, and it's E. And E is, of course, bigger than 1. It's around 3, like pi is. It's a little less than 3, about 2.72 something. Okay, but in any event, 1 over that is a number. Here's approximately what it is, but it's less than 1. That's the key. And of course, since that's less than 1, then this series right here must converge absolutely by the ratio test. So at this point, we're actually finished with the problem, but I want to use my sequence and series GeoGebra activity to examine the ratio test on this problem. And here, I used this activity before. Let me see if I can pull this up. Okay, here it is. I don't need two sequences here because I'm not comparing them, but I can do k factorial over, let's do k factorial over k to the k power. Yeah, there it is. So here's our sequence of Here's our sequence of the underlying sequence. Of course, it's approaching 0. The sequence of partial sums is coming up like this, and it looks like it's approaching something in the vicinity of 2 for the sum. And here we see the sequence of partial sums worked out here. So it looks like it's approaching something around the lines of 1.87985 to that many decimal places. Sequence of partial sums there. This is the sequence of the underlying terms rounded off. Don't worry about D and E. That's just dealing with another sequence we don't need. But then we have the ratio test right here, and this is looking at what those ratios of terms are looking like. So if we divide the, I guess it's dividing the second term by the first term, we get a half, 0.5 divided by 1. And then we divide the third term by the second term, we get 0.4 repeating. And divide the fourth by the third, we get this, and so forth, and then do an absolute value. This one's all positive terms anyway to begin with. But anyway, we work this out, and we can see that this is approaching a limit. Okay, it looks like about 0.36973. It's actually approaching that limit of 1 over e. Okay, so we're not quite. We've got several digits of accuracy so far. So in any event, I wanted to just show you this this sequence and series activity, and notice that you can put in 2 series here. It will do the sequence of underlying sequence here, the sequence of partial sums here and here. It will do a limit comparison test there. Remember, in the limit comparison test, you're doing the ratio of the sequence of the known one would be the B one divided by the one we're looking at, which is the A. So you know, here, for example, would be 0.3 repeated divided by 0.2 repeated here if we were comparing to 1 over k, which we're not here. And then the ratio test is within a series. It's comparing a ratio of one term to the next, and you can see that worked out here. Okay, and so that gives you some idea what's going on there. And of course, we can look at the sequence of partial sums and the underlying sequence there. All right, moving on to the next example. 2k factorial over k to the 6th. We're going to expect this one to diverge. A factorial is going to grow faster than the power function. In fact, the limit of the underlying terms is probably not even 0, although that may be a little more difficult to work out with the factorials. Okay, so we would probably expect this thing to go to infinity. In fact, it does. So let's work that out. So we look at where the k, first of all, this the whole thing is the denominator, right? Then you take this, where there's a k here, put a k plus 1. And where there's a k, put k plus 1. That's in parentheses. So this 2 to the k goes in the bottom, 2k factorial goes in the bottom, the k to the 6 goes to the top. This k plus 1 to the 6 is in the bottom, and this thing, 2 times parentheses k plus 1, then close parentheses on the whole thing, factorial is there. Now this is inside the parentheses, so you go ahead and distribute here and get 2k plus 2, and that's factorial, like that. Now, 2k plus 2 factorial is 2k plus 2 times 2k plus 1 times 2k, 2k minus 1, 2k minus 2, and so forth. Well, the 2k on down is 2k factorial, so that's going to cancel with what we got in the bottom. We still got these two terms here in the top. And then we've got a k to the 6 and a k plus 1 to the 6. Well, if you look, 6, 7, we've got an 8th degree polynomial in the top and only a 6th degree in the bottom. That's going to go to infinity. I was able to drop the absolute values because everything is positive here. So that definitely diverges by the ratio test. And here's the illustration here. This one, the sequence of partial sums is just it's just diverging to infinity. The ratio test is always the first test that will be used in finding intervals of convergence for power series, which we will get to in a few pages or in a few videos down the line. So the ratio test is one that we will end up using a lot. So hopefully there's enough examples there that you can supplement ones that you might find in your textbook and allow you to get some homework problems done.